Hey guys, it's Malta here, and in today's video, we're going to learn how to evaluate a one-sided limit, along with identifying some of the similarities and differences that a one-sided limit has when compared to a standard or normal limit. So without any further ado, let's get into it. Now, the first thing I want to put forth here is that we need to all be on have the same sort of knowledge base when we do these problems. And so I have some, notes that we can refer to. And so the first statement that I want to make sure we all have is that continuous means that the limit exists and it is the same as the function's value. And so this statement is really just trying to dictate that if we have a continuous function, we're going to have a limit, we're going to have limits that are going to be able to be found throughout the function. But the second part of this statement is going to tell us that, okay, let's say we have a function value that's 3, 5. So a point on the function is 3, 5. This means that the limit as x goes to 3 is going to also be 5. Alright, so that's established. Now our next point here is we have some types of discontinuity that we have to address. We have two types of discontinuity. We have removable and we have non-removable discontinuity. So removable discontinuity only takes form in a hole. So if we have a hole, it's going to be a removable discontinuity. Non-removable discontinuity can come in a jump. And so in a jump, we have a function that approaches two different y values from the left and right. If you look on a graph, you'll see that there appears to be a jump. The graph goes from, let's say, -1 and bumps up to 1. And then we have an infinite discontinuity, which takes the form of a vertical asymptote. Now, the last thing I want to address here is cusps. And so a cusp is any sharp corner on a graph. And so a sharp corner will generally occur when you have, let's say, a piecewise function, in which, let's say, you have a parabola at, let's say, -1, and then also at -1, you have a linear line that's starting. And so it looks, there's a sharp corner that appears there. And so the key, note of importance with the cusp is that limits do exist at these points. Alright, so with those pieces established, let's get into some examples. So in these examples here, we're going to be using the graph to determine the limit, and then we're also going to be discussing the continuity of the function. So let's actually take out that second part first. So if you look here at this graph, we have a linear line. It's going through the point 4, 3. And so if we're looking at continuity here, we'd say, well, this is continuous. There's no breaks whatsoever. So this is continuous. Now, if we look at part A here, we're being asked to find the limit as x goes to c plus f of x. And so you might be saying to yourself, what is c plus? And so what I'm going to say here is c plus basically just means that we're going to be evaluating the limit as x goes to c from the right of f of x. So what this means here is our c value in this case is right over here. C equals 4. And throughout these three parts of this problem, c is always going to be 4. And so when we look at part A of the limit as x goes to c plus, we're looking at the limit as x goes to c from the right. So this means that we're going to be looking from here to here. And so we're going to be saying, okay, let's say we start at 5, x is 5. Let's go to, x is 4.5, x is 4.25, x is 4.125, just trying to get closer and closer and closer to 4 to evaluate from the right what that limit's going to be. Now in this example, we're pretty fortunate because this is a continuous function. And so we actually do have a value at 4. It's 3. So we can actually say in this case, the limit as x goes to c, or 4, from the right is going to be just 3. And this is really the easiest type of question that we're going to be faced with. Now from the left, all this means is instead of saying let's go from 5, to 4.5, let's say, okay, let's go to 3 to 3.5. Let's go from values a little bit under 4 and try and get ourselves closer to 4. So once again, we're going to be following in the direction of this arrow. We're going to be going from values a little bit under 4 to trying to get as close as possible to 4. In this case, we can reach 4. And so once again, because this is continuous and we're already told that at 4, our function value is 3, we can say that the limit as x goes to c negative, or as the limit as x goes to c from the left of f of x is also 3. Now for part C here, we're looking at the limit as x goes to c of f of x. And so because we know, as we've done previously here, these last two parts, we've looked at from the left and from the right. And so because of that, we know that we can evaluate this limit because it's the same value from the left and from the right. And so because it is, we can say that this is simply 3. So this is just really just using our past knowledge. We could have done this in the last two sections. Actually, if you look at the function here, if we look at x is 4, if we look at from the right here, look at from the left, yeah, in both instances, we're going to 3. So that's why we can easily evaluate that limit. All right, so here's our next question, and this is more of the same. It'll just look a little bit more complicated. It looks like a sine or a cosine graph. One of those two, it's been magnified by a factor of 2. If it's a sine graph, it's been translated a bit. But regardless, let's just look at the continuity first. So once again, we're looking continuous over this whole interval. So that's good for us. Now, part A here, we're being asked the limit as x goes to c plus f of x. Now, this means, again, that we're just evaluating what's the limit as x goes to c from the right of f of x. So in this case, c is negative 2. And if we're looking from the right of negative 2, we're going to be going this way. So we're going to be looking at values that are, less negative of negative 2, and then going closer and closer and closer to negative 2. So we'll be looking at, let's say, negative 1 to negative 1.5 to negative 1.75, all the way closer and closer and closer to negative 2. But thankfully, this function is continuous. And so that means that we can just use the function's value here of negative 2 comma negative 2 to evaluate that the limit as x goes to c from the right of f of x is just going to be negative 2. Now, for this next one here, we're looking at the limit as x goes to c from the left. And so, as we did in our last problem, this means that we're going to be looking this way. We're going to be looking from values that are more negative to our negative 2 value. And so, once again, function is continuous. That's good for us. This means that we can just use the function's value to evaluate what the limit is as we go from the left. So, in this case, as we go this way, follow the function down, we'll see that, hey, guess what? Once we reach negative 2, we end up with a value of negative 2. And that's our answer. All right, now we just have our standard limit. So if we look at negative 2 here, from the left and from the right, yeah, it's going to negative 2. And so we can evaluate that. If it's continuous, what that means is the limit, our standard limit, is going to be the same as our limit to the left and our limit to the right. So there we go. All right, so now in our next example here, it's going to be a little bit more complicated. We're going to see a hole. And so in this question here, we're looking at a function that obviously isn't continuous. It's got a point of discontinuity at a value of 3. And so that's important to note because that's going to affect how we do this a bit. So begin with part A. We're looking at the limit as x goes to c plus f of x. So what's the limit as x goes to c from the right of f of x? So looking at it again this way. We're following the path of trajectory. And so as you can tell, if we follow this path of trajectory, we get closer and closer and closer to 3, we're going to end up with a value of 0. We discard this point up here because even though at a function value of 3 we're at 1, we're evaluating the limit. We're seeing as we get closer and closer and closer to 3, where are we ending up? And we're ending up at 0. All right, part B here, just from the left. So line of trajectory goes this way, following this arrow. Well, if we follow the arrow, guess what? Once again, we're going to end up with a value of 0. Alright, so now we have to find the standard limit. Limit as x goes to c of f of x. Okay, well, if we see here, from the right and from the left of c, we ended up getting values of 0. And so because with a limit, you're trying to look at where is it going from the left, where is it going from the right? Because both of those values give us 0, guess what? The standard limit is also 0. So as you can see here, the whole did not change too much. Just added basically just another layer of complexity for us to deal with. Alright, so in this example, we have another function that contains a hole. This time we have the hole at a value of -3. And so what this means here is we're looking at, in part A, what's the limit as x goes to c plus f of x? So what is the limit as x goes to c from the right of f of x? Okay, well let's draw a line of trajectory. If we're going from the right to c, we're going this way. And so what this means is if we follow this, we'll say, okay, so we go from -2 to closer and closer and closer to -3, guess what? We're going to end up with a value of 3. So we just get 3 here. Part B, we're just looking at it from the left. So we go this way. We follow our line of trajectory once again. And guess what we see? Hey, we're going to a value of 3 again. We don't look up here at this 4, because if we're just following the path of the function, we would not say, oh, we're going to skip up to 4. We'd say, guess what? We're going to go, and it looks like we're going to go to 3. So once again, we're at 3 here. Now, because from the left and from the right, we're at an equivalent value, we can easily figure out the standard value of this function. And so this, once again, is going to be 3. Even just using our knowledge that we had from the last 2 sections, disregarding everything we know now, we could say, yeah, I mean, look, from the left, from the right, yeah, we're going to 3. And so that's why we can say limit as x goes to c of f of x is indeed 3. Alright, so here we're facing a bit of a different kind of obstacle. We're facing a jump discontinuity here. You can see at 2, we're at 3, but here again at 2, we're at -3. So we have this difference of 6 that occurs virtually out of nowhere. And so we're going to have to try and do something to account for this. So in terms of continuity here, we have a jump discontinuity that's present at an x value of 2. But in this case, in part A, we're just looking at the limit as x goes to c from the right of f of x. So if we look at c, which is 2, because that's what the problem has stated out here, if we look from the right, we're going to be looking this way. Values greater than 2, so like 3, and then we're trying to get closer and closer and closer to 2. So if we look from the right, we'll see that, hey, guess what? We're going to -3 here. I mean, if we just follow this line trajectory, yeah, we're staying constant at -3. So we can say here, we can positively say this is -3. Alright, now what if we do it from the left? From the left, let's say from 0 all the way out to 2. So we're following this line of trajectory. Guess what? Once again, we got a constant value here of 3, and that means if we're following this line of trajectory, we're going to end up with the value of 3. Now, this is where it gets a little bit more complicated, because now we're asking for the limit as x goes to c of f of x. As you can see, from the left here, we're at 3, but from the right, we're at -3. Those two values are nowhere near each other, and so as a result of that, we cannot get a value of the standard limit as x goes to c. So we'll just abbreviate this as DNE, which is just shorthand for does not exist, because the limit, simply put, does not exist. Alright, here's another instance of a jump discontinuity. If we're looking at the continuity of this function, guess what we would say? We'd say, look, at -1, we have jump discontinuity. That's a bit of a problem. And so what we'd say here is, in terms of the continuity of this function, we have jump discontinuity at -1. Okay, now let's look at part A. Limit as x goes to c from the right. So from the right, we're going to be looking as we go from 0 to -1, because our c value is -1, as is established right over here. So as we go from 0 to -1, get closer and closer and closer to -1 from the right, we're going to see that we go to 0. So this is a value of 0. Alright, part B. Just the same thing, but looking at it from the left of C. And so actually I should have drawn an arrow previously, but it's just the arrow's following this line of trajectory. Now for part B, the arrow's following this line of trajectory. We're looking at it from values that are more negative than -1. So we're looking at, let's say, -2, and then getting closer and closer and closer to -1. And so if we follow that path of trajectory, we're going to end up with a value of 2. Never mind that there is a hole at -1, -2. It's still a value of 2. Alright, now once again, as we had previously, we have a jump discontinuity. This means that, well, we can't find the standard limit. From the left and from the right, we have varying values. From the right, we're at 0. From the left, we're at 2. That's a problem. So, once again, we get that this is DNE, shorthand for does not exist. Alright. Next up, we're done with the graphing stage of things here, and now we're just going to be trying to find the limit. And if we can't find it, we're going to have to explain why. So to begin with, this is a pretty simple problem, because even though this is saying what's the limit as x goes to 8 from the right, we can just evaluate this as, let's say, what's the limit as x goes to 8. Because all that we have to do is just do some direct substitution and replace this x with 8. And so if we replace x with 8, what will happen is we'll get the value of 8 plus 8, 1 over 8 plus 8. So that's 1 over 16, and that's in fact our answer. And so as you might see here, all that we had to do is we just had to make this connection that, hey, if we can find the standard limit, guess what? Then that's going to be the same limit as the value from the right. That's also true if we're looking at it as the limit of the value from the left. So that's all that we did here. All that we recognized was, hey, guess what? This is a continuous function here. If you graphed it out, you'd see it's continuous. And all that you got to do is you got to say, okay, we're going to do direct substitution as we've done before when evaluating limits. And this is how we can find our limit from the right. So this is really, in more formal terms, this is the limit as x goes to 8 plus 1 over x plus 8 is indeed 1 over 16. Alright, so there we go. Now our next problem here, we have limit as x goes to 5 from the right of x minus 5 over x squared minus 25. Now this might seem a bit familiar, and it should, because we've been dealing with these types of problems in our last section. So what we're going to do is we're just going to treat this as if it's the limit as x goes to 5 of x minus 5 over x squared minus 25. Now, one problem that we're faced with is that if we try to do the method that we did before of direct substitution, we'd end up with 0 in the numerator, which is all fine, but in the denominator we'd end up with 5 squared minus 25, which would yield a value of 25 minus 25, which is 0. And so whenever we have division by 0, that's a problem. So we can't evaluate our limit there. And so we're gonna try a technique that we did before. So we're going to do a bit of factoring here. So this limit as x goes to 5 of x minus 5 over x squared minus 25, we can just make this the limit as x goes to 5 of x minus 5 over x plus 5 times x minus 5. And this is really helpful because now at this point we can eliminate this x minus 5 factor in the numerator and the denominator. And so we're left with the limit as x goes to 5 of 1 over x plus 5. And so direct substitution can be used to solve this problem. And so we get in this case that we're just going to have 1 over 5 in parentheses plus 5, which is equal to 1 over 10. And that's indeed our answer. So if we're writing this out, we can say that the limit as x goes to 5 from the right of x minus 5 over x squared minus 25 is in fact equal to 1 over 10. So as you can see here, the techniques and fundamentals that we learned to evaluate limits in our last section can still be applied to this section. Alright, so here we go with our next example. We're dealing with the limit as x goes to -3 from the left of x over the square root of x squared minus 9. Now, before we actually jump into this question, I want to provide just a quick little rough sketch of how a graph of this function would look. And so it looks something like this. So there, right here is our y-axis. Here's our x-axis, like so. And if we were to graph this, we'd find something that looks a bit like this. And this is -3 here. And we'd have something that looks a bit like this. And this is +3 right here. And so what you'll see is, we're only worried about here the -3. But as you'll see, if we look and try and evaluate -3 from the left, so our like angle of trajectory is this way, we're following it this way, we're following the function this way, what we'll see is, we might say, oh look, we can evaluate this right here, you know, we can figure out this y value. Sure, we can evaluate this one-sided limit, but the answer is we can't, because in reality, this goes all the way down. This just drops down to -infinity. And over here, if they asked us, let's say, the question of evaluate the limit as x goes to 3 from the right, we'd be faced with the same problem, because once again, this really goes straight up to infinity. And so at the moment, we cannot answer this question. And so we're going to have to leave this as dne, does not exist. So we get the limit as x goes to -3 from the left of x over the square root of x squared minus 9 is dne. Does not exist. Simply because we're decreasing without bound. We're going to -infinity, but we don't know what the value is. Alright, so here we go with our next problem. In this case, we're looking at the limit as x goes to 0 from the left of absolute value of x over x. So in the numerator here, this is an absolute value of x. Alright, so to approach this problem, I want to point something out here with absolute values. And so what I want to make sure that we are aware of is that we can actually rewrite this as x over x if we're looking at x is greater than 0. And so the reason why we can do this is, if we think about it, let's say with an absolute value, we picked a value of 2. So if we put 2 into the absolute value, we end up with 2 again. And so that's essentially just x. If x was 2 and we put 2 into the absolute value, we get back 2. So x really just stayed as x. So we can make the absolute value of x here, when x is greater than 0, just be x. Because the same is true for 1. The same is true for 0.1. The same is true for 10. Alright, but now let's say we put in -10. Well, if we put -10 into the absolute value, we get a value of 10 out. And so what this means is that we're going to really have negative of x over x when x is less than 0. Because whenever we put a value that's negative into the absolute value, we get the opposite back out. So if I put -10 right in here, and we have this negative that we have right over here, negative to negative makes it positive, so we get 10 over x. And if we put -10 into absolute value, guess what? We'd once again get 10 over x. So we can rewrite this bit of a function here as this and make it piecewise. Now this is important because in this case, we're looking at the limit as x goes to 0 from the left. And when we're looking at finding a limit from the left, this means we're looking at values that are negative, that are less than the limit in question. So that means we're going to be looking at this part of the problem. And so what this means is, if we have negative parentheses x over x, this is the same thing as negative x over x. And this reduces down to -1. Now this is true every time x is under 0. And for the limit we're evaluating, x as x goes to 0 from the left, that's going to be true. Basically, x less than 0 is synonymous with the limit as x goes to 0 from the left. And so we can evaluate this limit as actually being -1. So we can say that the limit as x goes to 0 from the left of absolute value of x over x is indeed -1. Alright, so that's really just kind of the trick with absolute value. So with absolute value here, what you want to do is you want to say, okay, where is the breaking point? At what spot will the absolute value have an impact? And so what we can see is here, if we go positive values just with an absolute value of x, it's not going to do anything. The value is going to remain the same. But as soon as we go negative, guess what? The absolute value is going to flip the sign. It's going to force it to go positive. And so that's why we establish our breaking points at 0. All right, so here's our next question. We're looking at this time the limit as delta x goes to 0 from the left. The triangle here that you see is delta. And that's not really anything to worry about. Just consider delta x as just being a variable. You can think of it as just being, let's say, w. But in this case, we're just going to keep it as delta x. So in this case, we're looking at this limit as delta x goes to 0 from the left. And so what we're going to do here in this instance is what we're going to say is we have, what we're going to do is we're just going to try and evaluate this and forget that we have this limit from the left. So we're going to say we have really 1 over x plus delta x minus 1 over x. And we're going to say, all right, let's just do the subtraction. So we really have x times x plus delta x minus x times x plus delta x. And so what we're going to say is this is going to be equal to x times x plus delta x. And so all that we got to do is we divide here. We divide x times x plus delta x divided by x plus delta x. So we're going this way. And we get just a value of x, and x times 1 is x. And then we're going to do the same thing, but only this way. So what we're going to do is we're going to divide x times x plus delta x divided by x. And that's going to give us x plus delta x. Now let me make this x a bit cleaner here. Alright, so now we do the subtraction here. Guess what we end up with? Negative delta x. Alright, so now in terms of the overall problem, we're left with negative delta x over x times x plus delta x all over, and this is really in parentheses, all over delta x. And so this is really just dividing by a fraction. And so when we do division by fractions, what all this means is we're just going to get negative delta x all over x times x plus delta x times 1 over delta x. Because when you divide by a fraction, whatever you're dividing by, you're going to do the reciprocal of that. So the reciprocal of delta x is 1 over delta x. And this is extremely helpful because look, we got this shared delta x value. So you can just cross this out and we get negative 1 in the numerator over x plus delta x. Or actually I should say over x plus delta x times x. Now what we can do is we can employ our technique of direct substitution. So all that we got to do is we got to say negative 1, we really have this negative 1 here, let me just write that out, over x plus, in parentheses, 0, because we're replacing this delta x with 0, because x is going to 0, and then this is just times x. Alright, so what this does for us is this makes this negative 1 over x times x. So we can say that this is negative 1 over x squared. And what this means is that the limit as delta x goes to 0 from the left of 1 over x plus delta x minus 1 over x all over delta x simply reduces down to -1 over x squared. Now it is perfectly acceptable. It is the right answer that we have a variable, this x squared, in the denominator. Because we're dealing with a function that has two variables, we have the delta x, we have the x, we're only able to eliminate one variable, the delta x, and we've gotten our answer. So this is what we're supposed to get here. Alright, so here's our next example. We're looking at the limit as x goes to 3, 3 from the left. So we're looking at x goes from 3 to the left, f of x, where f of x is this piecewise function. This x plus 2 over 2, x is less than or equal to 3, and then 12 minus 2x over 3, x is greater than 3. And so in this type of situation, what we have to be able to do is we have to say, all right, we have piecewise. Is there continuity? Because if there is continuity, then we can easily figure this out. If there's continuity, we're going to have our standard normal limit, and then guess what? That's going to be the same as the limit from the left and from the right, and that's going to give us our answer. So the way we're going to check this continuity out is we're going to say, okay, here's the first part. Here's the first part of the piecewise. So our breakage here is at 3, because this is less than or equal to 3. This is greater than 3. So if they match up at 3, guess what? It's continuous. So let's test that out. So the first part, we're going to say 3 in parentheses plus 2. We're just going to do direct substitution. We're just going to replace this x with 3, and then we're going to make it over 2. So this is going to result in 5 over 2. All right. So as we can see here, this is 5 over 2. Now let's test out the second part of our piecewise. So if we put 12 minus 2, direct substitution for the x with 3 over 3, guess what we get? We get a value of, in this case, 12 minus 6, which is 6 over 3. And the problem here is, guess what? We end up with a value of 2. 5 halves and 2 are clearly different. So that means this isn't continuous, and so we're going to have to try and find a different way to solve this. And so thankfully that exists. All we got to do is we got to look back to the problem. We're looking at the limit as x goes to 3 from the left. So that means we're looking at it when x is less than 3. And thankfully, the piecewise function that we have been given provides for this. As you can see here, guess what? We have x is less than 3. That's represented by this function. So we can use this function to actually figure this question out. And all I got to do is say, okay, we can just put 3 in here, plus 2 over 2 equals 5 halves. And so that is going to be our answer. So what we have actually is that the limit as x goes to 3 from the left of f of x is 5 halves. And so as you can see, when we tried seeing if it was continuous, it didn't work out. But thankfully, the way that they had these piecewise functions set up, we can actually evaluate this one-sided limit just by going back to 1/2 of the piecewise. Alright, so here's our next problem. We're looking at a very similar one here, another piecewise function. We have the limit as x goes to 1 of f of x, where f of x equals the piecewise x cubed plus 1, where x is less than 1, and x plus 1, where x is greater than or equal to 1. So once again, let's say if we wanted to see if this was continuous. What we do is we put a 1 in for x. We do some direct substitution. We get 1 cubed plus 1. Well, that's just 2. Then we do a similar thing here. We'd get 1 for the x plus 1. That's also 2. Well, guess what? This is continuous. So that means our standard normal limit exists. And that's great because that's what we're exactly trying to find. We're not doing a one-sided limit this time. We're looking at our standard normal limit. And because this is continuous, we can evaluate it. And even better yet, we've actually solved it already. Because as you can see here, we found that as we go for a value, function value of 1, we end up with 2. So the limit, actually, of x going to 1 of f of x is indeed 2. So there we go. That's our answer. And so all we got to do in this case is we just have to realize that, hey, guess what? We can confirm that these piecewise parts are continuous, which we needed to do because the limit we wanted to evaluate was where there could be a possibility of discontinuity. So we proved that there was no discontinuity there by doing this work here, and in turn we actually figured out what that limit as x goes to 1 in fact, a rough sketch of the graph. Now before I actually do that for you guys, if you don't know, cotangent of x is just equal to 1 over the tangent of x. So if you're looking to graph this on your calculator, all you got to do is in the y equals part, you just got to write 1 over tangent of x. And so here's just a rough sketch of what I found. So if we graph out cotangent of x, or 1 over tangent of x, I found that if we just mark this important value here of pi, because that's what we're looking for the limit as x goes to pi, what ended up happening was I got a function that looked like this. It went down here, and then at pi over 2 it reached 0, and then it changed and it went like this. Something like that. That's just a rough sketch. And then over here, we make another, at 3 pi over 2, it went to 0 again. And once again, it looked like this. It went down, it went across, it hit this part here, this point, and then it went round like this and down. And so what we can realize from this is if we're just looking at the limit at pi, what we will see is, as you might notice already, the problem is we have this infinite discontinuity. This really goes down to negative infinity here, and this really goes up to negative infinity here. And so these are really both at pi. And so the problem that we have is we have no set values. I mean, in one instance we're down here at negative infinity, and in the other instance we're up here at positive infinity. And so that's an issue. We can't evaluate the limit if we have this sort of discontinuity. So what we end up saying is the limit as x goes to pi of the cotangent of x is equal to dne. It just does not exist because of that discontinuity. And so that's really all that we can do in this type of situation. Now, the one thing I would take away from this, and I'll make very clear, if you see a trigonometric limit, definitely graph it. Makes it a ton easier to graph it. Alright, in this example we have the limit as x goes to 4 from the left of 5, and then in this 2 brackets x minus 7. Now if you're wondering what these double brackets mean, is it just indicates that we're dealing with a greatest integer function. And so a greatest integer function I like to handle in the same way as a trigonometric function. And so what we're going to do is we're going to first make a rough sketch and then try and evaluate this one-sided limit. So here's the y-axis that we have, and then here's our x-axis that we have. So this just runs like this. And so what I'm going to do is, because whenever I make a solid filled-in circle, we get sort of, I guess, like a error message. What I'm going to do is I'm just going to make a star, and so this is just going to represent a filled-in circle. So here's our little star, and so this from here to here, and this is just all of 0. So whenever we put 0 into this function, we're always left at negative 7. But then, once we go to a value of 1, once we put 1 into this function, we end up going up to negative 2. So we'd be about here-ish. And we'd go like this, and we'd carry this out. And so this right here would be at negative 2. So this is for x is 1, this is for x is 0. And then, if I extend my x-axis out here, if we go up here and we figure out this greatest integer function at x is 2, we end up being here at 3. So we're going to make the star here, and this is going to go out. We're going to have an open circle here. This is going to be at 3. This is going to be at x is 2. Alright, so then we're going to do this again because we have to get to the limit as x goes to 4. So now we go up here, we're now looking at a y value here of 8. So we're going to be here with our star, we're going to be going out, here's our circle, we're at 8 in y value, and this right here is x equals 3. And then now what we have is, now we're going to get to the value we want. So we're going to be at a function value of 4. So we're going to have our star here, and then we're going to go out. Here's our circle, and then we're going to be at 13, and this is when x equals 4. And so what we have here is, this is just our step function. And one thing that you'll notice with the step function is that the function value that we put in, so when we put in 0 down here, we remained at a constant value of -7 until we got right to our next value of 1, at which we jumped to -2. And the same thing happened again and again and again. And so this is important to note when we're evaluating this function, because when we're looking at evaluating the limit as x goes to 4 from the left, we're going to be looking at the function value when it's just a little bit south of 4. So when the function value is, let's say, at 3.9 or 3.99. And so in that case, we're going to be over here. And so this is important because we're going to be looking this way, following this line of trajectory. And so what we can see here is, if we follow this line out, basically when we get as close as we can to 4, which will be here, we're going to be at a value of 8. So in this case, our answer is going to be, to this question, is going to be the limit as x goes to 4 from the left of 5 times here, this -7, is going to be 8. And that's going to be because as we look and we're to the left here of 4, because this is our x value of 4 here, is we're to the left, guess what? We're over here, we're at 3.9 or 3.99, and guess where that takes us? That keeps us constant as we go from 3 to 4, that keeps us at a constant 8. So as a result of that, we're going to be having a limit as x goes to 4 from the left of 8. And so we're not going to go up and look at 4 here, we're going to look and be to the left of it because we have this jump discontinuity. We're not continuous. And so that's why we're specifically going to look on sort of this angle of trajectory here, just looking at, going from 3 to 4. And that's going to give us a value of 8. Alright, well, thanks for watching. If you liked the video, leave a like. And if you want to see more content like this, definitely would appreciate if you wouldn't mind subscribing. So thank you for watching, and hopefully I'll see you in our next video where we will be continuing these one-sided limits and evaluations of continuity with functions.